Good evening, everybody. I'm Kartik Kulkarni. I'm a co-founder of Akash X, and we are building what we call storage accelerated lakehouse engine. Um, so storage acceleration is a technical approach that we are taking to improve the cost performance when you run SQL workloads on your data warehouses and lakehouses. And I'll talk about that. Uh, but at the very high level, we see that a lot of innovation has happened on top of S3, right? It has assumed that S3 is going to be the state of art forever. And a lot of innovation would happen mostly on the compute side, but basically because everybody has simply sort of assumed that we will build on top of S3, storage itself, a lot of evolution that could have happened, in my personal opinion, has not happened, and then we are that's why we're taking this radical approach of diving into the storage side rather than the compute side. And today I want to share with you some of that approach and our learnings on how Iceberg and in general SQL workloads can be significantly accelerated if the innovation actually touches the storage side. Yeah. Um, so before that, just a little bit background about me. I have spent over a decade building databases. I used to lead an important team at Oracle called transactions team. So my team was responsible for a lot of things acid within the database. And my co-founders Darshan, was actually head of data for a couple of unicorn e-commerce companies, and also Chris, who was the chief business officer at Minayo. So before I dive in, quick thanks to some of our investors and advisors, Sam from MIT and David Devitt, famously or infamously known for the Devitt's clause, and also some of the investors that have backed us. So open table formats have clearly arrived, right? People hate proprietary internal formats for various reasons, including the not having vendor lock-in, or also because a lot of data integration and innovation can happen when the data is unlocked and unchained and free, right? So and Iceberg seems to be taking the lead, at least because we are in this particular meetup. But my observation is that the engines are really headed for the iceberg. There's a Titanic reference here, if you couldn't catch. So what I mean by that is, when you look at the evolution of the databases and the database engines, there are decades of optimizations that have evolved over the time, right? And a lot of these optimizations, at least in databases technologies that were built over the past, have relied on either the internal storage formats or the internal storage engines. Now, if you ask them or put them in a situation where, hey, there's this brand new open table format, and by the way, it doesn't live on your storage engine, it lives on some other storage engine, and you got to run on that. Um, what happens is that the existing engines, developers are trying to evolve their engines to obviously make it work on these new open table formats on this disaggregated storage layer. But those optimizations that relied on the internal formats and internal storage engines have somehow been lost. A lot of optimizations around exploiting the data locality, around co-location of data with certain compute, all of that is somehow not applicable in this new world, right? And there is a consequence to that. The consequence is you are paying in terms of cost performance. If you take any engine today, and benchmark it against its own internal storage engine or format, and then make it work on, let's say, Iceberg, I don't think you'll get the same performance. This is not to say that Iceberg lacks in terms of its ability to support the engines to have unleash their optimizations, but it just that balancing compatibility and performance on a new turf becomes a challenge for these engines, right? And also this direction itself is sort of as people refer to, is unbundling the database as such, right? I come from this OLTP world where a database actually did a lot of things, or mostly everything. Right from storing your data, indexing, like querying, any housekeeping activity that you had to do, like compaction, everything was basically done on a database, and you just use SQL to run on top of it. Now, you see there is this storage layer that's separated. There is this open table format data that lives. There's a different catalog. Then there is an engine, and to ingest there is another engine. To query there is another engine. So what happens is that when you have so many tools, and you're unbundling the whole database, a lot of your housekeeping activity, for example, gets sidelined, and that's why you had these Spark packages people used to run to compact the data, and now that has led to this S3 tables, I believe. So when you have this unbundled system and you package together different components, modularize and then build something, it's hard to make it a well-oiled machine, which databases used to be in the past, right? And it all adds up, right? And if you look into the deeper into the root cause as to why and how we came here, I'm not necessarily saying that this is a bad situation. There are a lot of advantages to this unbundled ecosystem. I would say a lot of cost and performance issues of this era dates back to the whole compute storage separation itself. Back in the day, when Amazon and said that S3 is going to be the layer where you keep all your data, and then you run OLAP engines or whatever it is for that matter on top of it. What happened was you made access to your data 1,000 times slower compared to a world where storage and compute were tightly coupled, right? And there is definitely a big advantage to it in the sense that you could evolve different layers independently, but you're also going to pay in terms of cost and performance. So what do today's OLAP engines do? Like the one we heard before, you parallelize access to the data, right? To overcome the challenges of both latency and throughput. You parallelize and then have many different cores. You either do that or you also resort to aggressive caching, right? Now, interesting thing about OLAP is that the working set itself is not very defined, and the query patterns are random, and you could end up having a huge working set. So if you rely on aggressive caching, your caching could actually your cache could be pretty huge, and your caching, remember, on these highly parallel machines, big beefy machines, compute machines, because you have to parallelize access to the storage. And not to forget, these compute machines are ephemeral. You lose them, then you have to recache, right? So all of these things add up, and the result is that your cost performance when running on data lakehouses is not the greatest, at least when compared to the previous days, right? So what we are doing is taking a slightly different approach. We call this as empowered storage architecture. We have a storage accelerated layer. We call this as ES3, as opposed to just S3. And empowered storage, the philosophy is that you swing the pendulum a little bit backwards. We went from tightly coupled storage and compute to a fully decoupled, disaggregated storage and compute, and we come back a little bit. We add a little bit more compute to the storage layer, and the storage layer is now capable of doing certain operations that are data reducing in nature and consume less compute, so that the fetch from the storage is not too much to overcome the latency, to overcome the throughput issues, to overcome the need for significant aggressive caching on your compute layer. So what ES3 is able to do is it is able to do partial filtering, simple partial aggregations, and certain data reducing operations, like, for example, look up the metadata and then access the data, which sometimes has to be done over the network. Now you push it down to the disaggregated storage layer and so forth. So the goal here is to reduce the data fetch dramatically when you access data over the disaggregated storage layer. And in doing so, the memory footprint would be lower in the compute side, the network utilization would be lower, and in general, you would need the smaller instances to execute the same or similar workloads. So that's the direction that we're taking. Now, ES3 itself can work as a fully, autonomous storage layer, or it can layer on top of your S3 and serve as a red hot tier, for accelerating analytics workloads. S3 itself has many tiers. Think of this as an extension layer or tier rather on your S3 if you're using it in a lakehouse mode. So zooming out a little bit, this is not new at all, right? Like, pushing compute closer to the data has always been, ancient wisdom in the database community, right? If you see most databases, they do push down of various operations within their own stack. If you look at Netezza, that was one of the first ones to push partial SQL down to the hard drives using FPGAs attached. Oracle Exadata, the team where I work for, we push SQL down to the file system level. And you can think of Hadoop as basically map-reduce compute pushed down to HDFS storage nodes. So what we are trying to do a little bit different is that we're pushing down partial SQL down to a disaggregated object storage. And this is relevant in today's world because when we talk about storage, people think of object storage. And this is especially important in the era of open table formats like Iceberg, because this form of acceleration where you're pushing down certain operations to a disaggregated storage layer is not dependent as such on any table format or file format. It's kind of agnostic. So for this optimization, so to say, to work, all you need is certain operations have to run closer to the data. It doesn't matter which format it is. And hence, this approach can accelerate access to open table format data. To give you an example, let's take a SQL query, select sum on a column, group by another column where customer country is equal to Germany. There is a syntax error in this particular SQL. Let me see who catches it, but that's not the point of this, this example. If you look at this query, the data reducing components in this query are the filtering, obviously, which is customer country is equal to Germany, depending on how selective this filter is. And also, this query is asking you for expression. It's neither asking you for rows nor columns. So it's actually doing a local sum. It's actually doing a sum, right? So we push down the filtered scan of local data and the sum itself to each local storage node, so to say, right? And what gets returned from the storage layer to the engine layer is an intermediate result rather than raw data. So in this particular case, if the filtering itself is like very very selective, then you end up retrieving a lot smaller payload from the storage layer. So how do you decide what to push down and what not to push down, right? If you push down everything to the storage layer becomes a database, right? And if you don't push down anything, then it becomes a data lakehouse, essentially. So that decision, the thumb rule for that is like, if there's an operation that can reduce the data fetch and that does not take significant compute, and it can exploit data locality, right? Those are the operations that we push down. And how do we do it? We basically augment the optimizer in the SQL engine to actually take this call. So it's actually a coordination between both the engine, SQL engine layer, and the disaggregated storage layer. So it's not 100% disaggregated. There's, as I said, the pendulum just swings a little bit, but not too much to the side of tight integration. So that's how we decide what to push down and what not. So yeah, I mean the product itself bundles the SQL, ANSI SQL execution engine layer on top of the ES3 accelerator, and it is provided as a SQL analytics infrastructure. So some benchmarking that we have done, obviously, because we're talking about the performance here, especially the cost performance. So we took a sample workload of about 10 terabytes and workload volume of about 500 hours a month. Typical, mid-tier organizations needs maybe to the smaller tune because it's like, people sometimes talk here in these type of events in petabytes. So if you use an extra large instance from multiple cloud data warehouse providers, The t-shirt sizes have somewhat become uniform, if not exactly uniform these days. So you're looking at a 338K in annualized bill for this type of workload. S3 is, thank God, it's very, very cheap. It's $23 per terabyte per month. So you're looking at something like 341K. So in our case, what we do is we actually add a line item to the bill, which is ES3. And ES3 is more expensive than S3 because it has more compute packed per unit data. So it costs about $60 per terabyte per month. And it is implemented as a combination of EC2 instance and the EBS or local disk. And hence there is no access cost involved here to the data. And what it does is it brings down the compute consumption in R extra large so much so that it ends up costing 68K with 100% markup and 50% gross margin. I'm just talking about sample unit economics. That's not necessarily our go-to-market strategy, but we can reduce the TCO by pretty big margin. Even adding the 50% gross margin is what our claim is. And this testing was done with TPC H and also TPC DS up to 10 terabytes volume range, data volume range. So we've had some interesting deployment use cases. One of the early adopters was this company called as Gordian, which is a cancer drug discovery company. They have an interesting problem in the sense that they work on dark human genome, which is basically majority of the human genome that is not very well understood. And they think the cure for cancer lies in that portion of the genome. So they do pretty significant compute-heavy workload, and we were able to provide them with this value proposition, and they're actually using us in their actual analysis and research data. So I'll just, in the interest of time, I'll just say that it's time to reimagine the whole storage side of the equation, and of course, the compute side. There's a lot of innovation. There are way too many products out there that innovate compute very interesting ways. But I think it's probably time to look in the storage layer. That's basically the message from me. Thank you.
All right, some questions.
So thanks. It's a nice presentation. So you compared Databricks versus Akash X, right? So do you guys build your Spark engine, or is a extension to Spark, or if you have to use Akash X, like what is the way?
Yeah, our goal is to basically support multiple engines on top. Our core innovation, as I said, is on ES3 side of the things, and then the changes to the engines on top is basically to push down operations. So yes, in that case, yeah.
Okay.
We also plan to. We are still iterating on what engine to have as our default engine. We're trying out with DuckDB. We're trying out with Spark, of course, and other ANSYS SQL engines. We will hopefully be able to resolve pretty soon. Yeah.
Okay. So is this also available on Google Cloud? We are on Google Cloud.
You're on Google Cloud?
Yeah.
Yeah. So the other approach that we're taking is we are purposely not taking a heavily multi-tenant architecture. So we are providing, we're choosing single tenant but elastic approach. So yes, we can deploy on any clouds.
Very good. Thank you very much. Thank you, Akash. Really, sorry, the Akash Cloud.
Akash X, yeah. Thanks.
So Akash, by the way, I mean, those of you who don't know, Akash is the sky and clouds are in the sky. So
yeah, the idea was that we want to elevate the standard of the cloud.
Yeah, raise the bar, of course. So really cool name. Thank you very much.
Thank you very much. Yeah.